Hi, in this video we are going to see the system action of an LTI system when the input is chosen as a periodic signal. Now the LTI system is shown as a black box. The input signal is x of t and the output signal is y of t. And the impulse response of our LTI system is h of t. Now just to review what we mean by an LTI system. LTI means linear and time invariant. Okay, linearity means if you have two arbitrary input signals, x1 of t and x2 of t are arbitrary input signals, and x1 of t gives us the output y1 of t, x2 of t gives us the output y2 of t. Then alpha 1 x1 of t plus alpha 2 x2 of t gives us alpha 1 y1 of t plus alpha 2 y2 of t, where alpha 1 and alpha 2 are arbitrary constants. Okay, so this is linearity, and time invariance means, okay, so this is an explanation of the fact that our system is linear. So this is the linearity definition. And for time invariance, remember, if x of t gives us the output y of t, if then x of t minus t0 gives us y of t minus t0 for any arbitrary t0. So this is the definition of time invariance. Okay, and remember the definition of the impulse response as well. Impulse response of our LTI system is the output when the input is chosen as an impulse. Okay. Now, up to this point, we have just reviewed some of the basic definitions related to LTI systems. Now, we also know that when we have an arbitrary LTI system, the output y of t is equal to the convolution of the input and the impulse response. So this is the convolution operation x of tau h of t minus tau integrated with respect to tau. So this is the convolution of x of t and h of t. So the output can be obtained by means of the convolution of the input with the impulse response in an LTI system. So we have also seen this before in another video. Okay, for the discussion related to periodic signals chosen as input signals of LTI systems, we need one more concept, and that is the concept of stability. Now, we first give the definition of stability. An LTI system, in fact, this is a more general definition for any system. An LTI system is said to be stable if any bounded input signal x of t yields a bounded signal, output signal y of t. This word any is important. So x of t is arbitrary. It can be any input signal which is bounded, which is chosen as a bounded signal, and this input signal must yield a bounded output signal. Now, what do we mean by a bounded input signal? The signal x of t is bounded if magnitude of x of t is okay, maybe we should write it first as in the following way. The input signal x of t is bounded if there exists m greater than 0 such that x of t is less than m in magnitude for all t. Now, magnitude of the signal is the absolute value of the signal for real valued signals and modulus of the signal for complex valued signals. But this is the definition of a bounded signal. So with this definition in mind, the definition of stability is clear. The system is said to be stable if any bounded input signal yields a bounded output signal y of t, corresponding that input signal x of t. Okay. Now next we have a result related to the impulse response. What can we say about the impulse response of a system? in relation to the definition of stability. Okay, so next we are going to see this, discuss this topic. Now, for a linear time invariant system, we have the following claim. An LTI system is stable if the impulse response h of t is absolutely integrable. That is, we have this condition from minus infinity to plus infinity, h of t integrated, the magnitude of h of t integrated must be finite. The integral must be a convergent integral. Okay, so this is the condition for stability. We can prove this as follows. Now we have to show that for any bounded input, the output signal is also bounded. Now remember that y of t is equal to, from minus infinity to plus infinity, h of tau x of t minus tau d tau. Convolution is a commutative operation, and therefore hx can be written in any order in the integrand. Okay, so magnitude of y of t is therefore magnitude of the integral of this expression, the convolution expression. Now, the magnitude of the integral is less than or equal to the integral of magnitude of the integrand, h of tau, and we can separate this into these two expressions integrated with respect to tau. Now, we know that we want to show the following. For any bounded input, the output must be bounded. So let the input be a bounded input. Therefore, there exists a certain constant, positive constant m, such that this term is less than or equal to m. Therefore, less than m, rather, we need only an upper bound. So we have from minus infinity, okay, that m can be taken outside the integral. So minus infinity to plus infinity, magnitude of h of tau integrated. But also we know that this must be finite. Therefore, y of t is also bounded, since h of t is absolutely integrable. Okay. Now we have a very important result related to stable LTI systems. I'm going to write it down also as a claim. In fact, these can be written as theorems if you wish. Now let x of t be an arbitrary periodic input signal of a stable LTI system, then the output signal is also periodic with the same fundamental period. So we have the following diagram. We have x of t, the LTI system, impulse response of the LTI system is h of t, and y of t is the output. This is periodic. X of t is periodic with fundamental period t0. Y of t is also periodic. It turns out to be periodic with the with also the same period. Okay, let me write it. With the same fundamental period t0. Okay. Now, how can we prove this result? Now, the proof is interesting because it is not only a proof, but it also gives us the method for the calculation of the Fourier series representation of y of t as well. Now, x of t is periodic with fundamental period capital T0. So x of t will have the Fourier series representation k from minus infinity to plus infinity ak e to j k omega 0 t. Here omega 0 is 2 pi over t0. Okay. So we have the Fourier series representation of the periodic input signal. So how can we calculate the output signal y of t, and how can we prove that y of t is also periodic with the same fundamental period? Okay, now let us look at the steps of these conclusions. Okay, now the input signal with the Fourier series representation k from minus infinity to plus infinity ak e to j k omega 0 t is the input signal of our LTI system. And corresponding to this input signal x of t, we are going to calculate, or our aim is to construct, if possible, the Fourier series representation of y of t. So how do we obtain the result? Also, we know that the impulse response of our system is h of t, and we have a stable system. So our system is stable. Stability is quite important in this discussion. Now, we can approach this problem in the following way. First of all, we see that the input, which is a periodic signal, is written in the form of a Fourier series, which is the superposition of the weighted complex exponential signals. Now, if we can calculate the output signal corresponding to any arbitrary complex exponential signal for arbitrary k, then we can use linearity of the system to evaluate the output. So our first step is the following. For an arbitrary k, let us consider the following problem. The input signal of our system is e to j k omega 0 t. Our system is the linear time invariant system, which is stable and with the impulse response h of t. So, how can we calculate the corresponding output? Let us call this input as xk of t and the corresponding output as yk of t, to just show the dependence on k. Okay, well, in a straightforward way, we just use the convolution integral. So yk of t is from minus infinity to plus infinity h of tau e to j k omega 0 t minus tau integrated with respect to tau. Now this is equal to the integral, convolution integral is with respect to tau, so e to jk omega 0 t can be taken outside the integral. E to jk omega 0 t is taken outside the integral, and the remaining integral is h of tau e to minus jk omega 0 tau integrated with respect to tau. Okay, now we ask the following question, which will give us the link to the stability of the system. The question is the following: is this integral convergent? I mean, can we evaluate this integral to obtain a finite value? In fact, the integral is a complex, will yield a complex value if provided that it exists, and the magnitude of that complex quantity must be finite. Okay, so we just look at the magnitude of this integral, h of tau e to minus jk omega 0 t integrated with respect to t. Okay, we look at this magnitude. This is less than or equal to the integral of the magnitude of the integrand e to minus jk omega 0 t integrated with respect to t. Now this term is equal to 1. Magnitude of the complex exponential is 1. Sorry, we have h of tau. Okay, the integration is with respect to tau. Omega 0 tau d tau, omega 0 tau d tau. Okay. So this integral becomes, so this expression is just from minus infinity to plus infinity h of tau integrated with respect to tau. Now we know that this must be finite so that we have a stable system. So this is this integral must be convergent and it must have a finite value. Therefore, yk of t is equal to e to jk omega 0 t, and then we have this integral. Now we know that this integral exists because h is absolutely integrable. So h of tau e to minus jk omega 0 tau integrated with respect to tau. Now let us call this integral h of k omega 0, because this will be a constant, a complex constant. So this is a complex constant in general. It can be real valued as well, but in general it is a complex constant. Therefore, if in our LTI system, but we have the condition of stability as well, if our input signal is e to jk omega 0 t, the output signal is h of omega, k omega 0, h of k omega 0 e to jk omega 0 t. Okay, this is the stable LTI system with impulse response h of t. The impulse response, as you see, plays a role in the calculation of this integral. So we have this important result. In fact, we have discussed this in another video to verify a very important result related to stable LTI systems. If the input signal of a stable LTI system is a complex exponential signal, the output is also the same complex exponential signal, but only multiplied by a constant. And that constant is a complex constant. Therefore, this means a change, the system action causes a change in the magnitude, okay? And also it introduces a phase, which is the argument of the complex constant. Okay, so as the first step in our proof or calculation, you see it is a proof and calculation at the same time, because we are going to construct y of t. In the Fourier series representation, we take just an arbitrary complex exponential signal among these harmonically related infinitely many complex exponential signals and apply this as the input signal of our LTI system, and we obtain the output. Okay, the next step will be to use linearity to obtain the output signal for the corresponding input signal. Okay, so we can consider this problem next. So step 2 will be the following. Now, we know that we know how to calculate the output corresponding to any individual complex exponential signal. So we know that x of t is equal to k from minus infinity to plus infinity, h of k omega 0, ak e to j k omega 0 t, and we know the system action when the input is chosen as e to j k omega 0 t. So let us show this by means of this arrow, which is in fact the system action. We have h of k omega 0 e to j k omega 0 t. So by linearity, if we multiply ak by e to jk omega 0 t by the constant ak, the output is ak h of k omega 0 e to j k omega 0 t. So this is the this is due to the fact that the system is linear. And finally, we have the superposition of all these harmonically related complex exponential signals, the superposition of these harmonically related complex exponential signals. So this, when we choose this as the input signal of our LTI system, so we apply this to the LTI system with impulse response h of t, and also we have the condition of stability. We have a stable LTI system. Then the output will be, by using linearity, we are going to observe the same superposition with the same constants, but also, of course, we are going to have the constant, complex constants, which gives us the action of the system, e to j k omega 0 t. But we observe something very interesting. As you see, this is our y of t, the output. But the output is also in the form of a Fourier series. So it is the Fourier series representation of y of t. Okay? And the Fourier coefficients are, let us show them by bk. The Fourier series coefficients of the output signal can be obtained from the Fourier series coefficients of the input signal by multiplying each k with the corresponding h of k omega 0. In fact, remember the system action corresponding to an input chosen as a complex exponential gives us the same complex exponential at the output multiplied by a constant. So remember that in the other video we have discussed this problem and interpreted it as the eigenvalue problem. So the complex exponential signals are eigenfunctions of stable LTI systems because the system action is just a multiplication or a scaling by a certain complex constant. Okay, as a result, now we have shown that, so this proves that y of t is also periodic because we have obtained the Fourier series representation. It's periodic with a fundamental period capital T0, the same fundamental period, which is related to omega 0 by means of this expression. We have not only proved that the output signal is periodic under the condition that we have a linear time invariant system which is stable, but also calculated the Fourier series representation of the output as well. Okay. Now we can just consider an example related to this. Now, to this result. Okay, let us choose our input as the impulse train. X of t is m from minus infinity to plus infinity, delta of t minus m t0. So we have the impulse train with a period capital T0. So x of t will have the Fourier series representation k from minus infinity to plus infinity. 1 over t0 will be the Fourier coefficients and e to j k omega 0 t. Okay, remember our previous discussions in some other videos related to the interpretation of this result. All frequency components are represented in the impulse train with equal weight, showing the singularity of the signal. So let us now consider this x of t as the input signal of a stable system, LTI system. So we have our LTI system with impulse response h of t, and let us choose h of t as follows. It is e to minus t for t greater than or equal to 0 and 0 otherwise. Now let us check the condition of absolute integrability. Now you see that this is a decaying exponential. Therefore, it is very easy to verify that h of t is absolutely integrable. Therefore, our system is stable because this absolute integrability condition is satisfied. So all we have to do is to calculate capital H of k omega 0. And this is equal to from minus infinity to plus infinity h of tau e to minus jk omega 0 tau integrated with respect to tau. So this is from 0 to infinity, because for negative values of t, h of t is 0. So we have e to minus tau, e to minus jk omega 0 tau integrated with respect to tau. Now this integral becomes minus 1 over alpha plus jk omega 0 e to minus jk omega 0 tau omega 0 tau evaluated at 0 and infinity. Now we have also here e to minus alpha tau in the integrand. E to minus alpha tau, okay, we have this integral. Now because of this exponential decay at infinity we will have 0, and therefore the result will be 1 over alpha plus jk omega 0. Alpha is minus 1, sorry. So we can write this as e to minus tau. Okay, so first I thought that we have e to minus alpha tau. Okay, so all these alphas will be replaced by 1. E to minus alpha tau, e to minus alpha tau, and we have 1 here. So we have 1 plus jk omega 0. Okay. So this means that our y of t will have the Fourier series coefficients bk, which is equal to 1 over t0, 1 over 1 plus jk omega 0. Okay, thanks for watching.